So welcome to the ICAPS community. I am Christophe Guettier, working with Edith on autonomous systems, and I'm going to present a work and some thoughts about planning and scheduling for onboard applications in aerospace and the safety and resilience applications. So SAFRAN context is ranging from many applications that involve autonomous systems. On the left-hand side, you have aircraft, standard civilian aircraft with pilots, potentially, that are evolving in known and master environment. And on the right-hand side, you have future systems like a UGV or a UAV or even civilian vehicles that are evolving on an uncertain environment, while the uncertainty and the contingency could be long-term for ground vehicles. For UAV, this is kind of mitigated, so we have a medium-term uncertainty and we have time to react. So in general, on the left-hand side, we model avionic systems with automata, and their behavior is completely defined by automata. And of course, we know how to do planning and scheduling systems for mission right now, but in the future, planning and scheduling will be performed on board, and it will have to be combined with automatic system scheduling, autonomous control, and planning for mobility. So while we knew how to validate and certify classical automata, now with these complex systems and with additional AI functionalities for reaching the appropriate level of autonomy, we have a real problem in verifying, validating, and certifying the system. So what is done in a classical engineering way is to model the system behavior as finite state automaton that is a determinist and reactive. So it means that from any state we have at most one transition and at least one transition. So it is always able to react to the environment stress. That is actually what is done for real-time and low-level control on a very short horizon. And this is in general also combined with a control law. For example, on this example, we have a SAFRAN ion drive that is heating maybe too much, maybe not enough, and we need to control the thrust level and depending also on the temperature level of the ion chamber. Now, what happens if we need to do autonomous control? Then we need to address a longer horizon, and we have no longer deterministic automata. So we may have transitions that can be either controlled by the environment or by the system. And we need to achieve a sequence of states that remains in a controllable envelope. So we have multiple possibilities to model that. One of these be done already is to model this as a constraint problem with states and transitions. And transitions could be constraints with variables that can be either problem variables or uncertain variables. Other approach nowadays could be investigated, such as using PDDL in version 2.2 and disjunctive temporal network with uncertainty. So planning and scheduling for mission is also important since it has to be performed on board and guide the vehicle on the long, medium or long term. And we need to address also mobility constraints such as the terrain structure or the flight level. And we need also to address onboard resources. Several actions can be realized, for example, by a UAV here. Observation of an area. If you investigate a disaster area and you try to locate survivors, for example, you need to position several potential actions in the environment to find these survivors. So an action structure typically would be at a given position for a given speed, and for at this time we would need to observe such area. And we would have to satisfy an onboard resources to be able to get back to the initial position. But also we have a post conditions that are important, the time duration of the action, but also the effect, whether we acquired a survivor and we can help the survivor or not. And we also need to update the resource consumption. We can solve the problem with several type of algorithms to generate navigation plan using classical A-star or D-star light if it's real time. We could use also dedicated planner in constraint solvers. We can hybridize search algorithms also with various techniques such as A-star and constraint heuristics. But also we can maybe develop the diagnosis part of the planning, meaning that there could be some preconditions with uncertainty and post-conditions with disjunctions that lead to several effects in the plant structure. So we could optimize the global plan to be safe by avoiding problematic disjunction, for instance, and then and therefore being able to go into fail operational mode if hazard cannot be avoided. The most important that could be done on a longer horizon, and the problem is to stack at the system engineering level all these planning problems, from the low level to the highest one. So we need to develop a real validation, verification and certification approach, starting on the left-hand side by all the algorithms, defining the strategy and integrating into an agent architecture. And finally, we need to execute the final software on the target processor. That could be FPGA, which is a classical use in aeronautics, but also maybe CPU or multi-CPU. But indeed, if you're doing some learning techniques for search or for planning, then you would go for a GPU. The FPGA architecture is certainly one of the most promising because it has some very good properties to certify. Nevertheless, we need to address the combinatorial explosion of the search algorithms to validate the global representation of the model and to also verify the behavior of the agent. But the main issue of executing all this software on the final processors is not addressed so far. In conclusion, we have three main areas to investigate. The first one being integration, verification, qualification, and certification methodology for these autonomous systems. And the idea to bound the functional domains over a future horizon is very interesting. For example, that was a temperature example in the flight control systems, or the flight envelope also for an aircraft. But we need to, of course, deal with model predictive control and actuation laws that are close to the physical environment. How to adapt these methodologies? Should we go to live testing and having a dynamic validation approach where we do real in-flight, for example, qualification of the systems? And also we would need to certify using the situational awareness of the environment, and that need to address the learning stages of the system. So what about performing a test drive to the complete AI system? That is a question. Another problem is to combine several planners and to have some good properties out to this combination of low-level planning systems and high-level mission-oriented level that provide different functionalities. We need, of course, segregated architectures to isolate the different planning level and to avoid fault propagation throughout the architecture. And we also need redundant architectures with a asymmetric implementation, both at functional and structural levels, which means involving several languages, several algorithms, several search strategies, maybe plan formalizations, and we need to achieve comparable performances to do that well. Lastly, we have a lot of opportunities by introducing these various levels of planning to diagnose and provide the prognostics of the failures over the horizon. has been explained, for example, in the engine system. And now, which hardware should be used? FPGA is certainly the most interesting because it's the easiest way to qualify a system. However, the need for learning or for multiple GPU to implement several functionalities would have to be addressed, and therefore solve the problem with operating systems to support the functions. Thank you for your attention, and I look forward to have your feedback on all these issues.